Stay in the corner of your desk here.
Because I was researching.
All right, everybody, I think I'm gonna go ahead and get started. I'm not sure where everybody is, but hopefully they're on their way. All this fog in the morning, I think makes, at least for me, it makes me a little lazy. I kind of go slow doing everything. So good to see all of you. I hope that your day is going good so far. I put up the Canvas webpage here. I just wanted to show you something here in the file section. You all got my email that I'm going to let you have that weekend, not next weekend, to study for the test. We're going to move. I hate doing that. I used to complain about other professors moving their exam dates around, but now I'm guilty of it myself. It's really mostly, I just want to make sure you have enough time to really study this stuff, because it is going to cover the first part of chapter 6, which we are barely even going to get to by today. Maybe I'll get to it, but more likely it'd be nicer if I get to it next week, and then you still have some time to learn this stuff. So our second midterm, it isn't too far down the line here. It's going to be on a week from Tuesday. So Tuesday, October 29th. And it will cover all of chapter 4, which is a lot. There's 10 sections in chapter 4. We only skipped one of them, which was 4.7. So you can skip 4.7, but the rest of chapter 4 will be there. All of chapter 5, there's only 3 sections in chapter 5. We're going to finish it today. And then 6.1, just the first section of chapter 6. So that is what the second exam covers. I would say chapter 4 would be roughly 50% of the midterm. Just on chapter 4, and then maybe we could break down the other 2 chapters roughly as 30% on chapter 5 and maybe 20% on chapter 6.1, something like that. That's a rough breakdown. But I wanted to just pull up the Canvas page here, because you can see there is a folder that's called Midterm 2 Resources. So if we open that guy up, you'll see here that I have a bunch of stuff in there already. So just like with our first exam, I have a sample midterm and its solutions. I have another sample midterm and its solutions. So there's 2 sample midterms. One of them's a lowercase version, one of them's an uppercase version. Just like with the first exam, I would recommend that you take at least one of them as a practice before we actually take the exam. Again, you have a lot of time. This will be like a week from now at least. But at some point, I would take a look at least one of those sample tests. And if you're not feeling too good about it by that point, you might try the second one also after you study a little bit more. So those are in there. There's also a review session, which has some additional practice problems. And I typed out the solutions to those problems. And then there's a packet itself. I need to update the packet just a little bit with my office hours and change the date and everything. So I'll update this review file here. But other than that, everything is good to go. You guys should be able to see this. And so if you're bored over the weekend and want to start looking into it, you can. If you go to the Pages section of Canvas, you'll see that there's a review session. I've chopped it up into a couple of videos here. So it's about 2 hours roughly. If you wanted to actually watch the whole thing through, you feel free to do that. And again, that review session lines up with the problems that are in this document here, review session for the second midterm. So I've got a bunch of stuff here, some practice problems, and those are the problems that I went over in that video, in that review session. So anyway, there's like 8 problems here that I have. See that problem number 7 right there? Find a basis for the span of, and then I just made a big long list of vectors. We just worked on that kind of problem Tuesday. I just have to throw out the vectors that are LD so that it becomes a basis. Yeah, so there's a lot of familiar looking stuff in there. But anyway, I just wanted to let you know that this folder is mostly ready to go. I do need to update the actual review, packet thing with the new date for the midterm and office hours and stuff like that. Other than that, this is all totally good to go. Any questions on that?
Do we get extra credit if we show up in a costume?
In a costume? Oh, is that, it's a little early, isn't it? I could move the exam to the 31st and then it would be, that would be really scary, right? We could add to the Halloween vibe. So, no, that's, a good point. Maybe we'll have to come up with a Halloween themed question somehow. I don't know what that would look like. I'll see if there's a way to put some linear algebra together with Halloween. But yeah. Any other questions before we get started today? There is a homework assignment due tonight. I've had a few people coming by already to ask a few questions. There's a place on my sideboard over there to add some problems, and you can do that during the break today. So we'll have a 10-minute break in a little while, and you can add some problems, and we'll try to work on some of those together. I'll help out as much as possible, and I have office hours, as you know, on Tuesdays and Thursdays. Later in the day, I'll be around to answer more questions. So I'll be glad to do that. But let's see if we can kind of finish up chapter 5. I know it feels like we just started chapter 5, but it's a short chapter. And of course, we're talking about inner product spaces. Okay, so let's just remember what this is all about. We have a vector space, right? One of our universes that we've been learning about for a few weeks now. And within that vector space, we would like to create some geometric notions, such as angles between vectors or the length of a vector, things like that, because after all, we can do stuff like that in R2 and in R3, and we have many other vector spaces that we could try to hopefully do the same thing. And so we define what is called an inner product space. It's just a vector space that has this inner product on it. The inner product just takes two vectors from the space and spits out a number. Basically, that's what it is. And there are a bunch of axioms that those the inner product has to satisfy for it to be valid. There's quite a bit of that in the homework that you're working on for tonight. So maybe if some more people have questions on 5.1, I can review those axioms again in a little while. I think for right now, I'll just kind of leave it at that. But if we have this inner product, then we can start talking about geometric notions, ideas from geometry, such as when are two vectors perpendicular to each other or orthogonal to each other, in other words. So V and W are orthogonal if their inner product is 0. It's just that easy. Just that easy. So you calculate the inner product of those vectors, and if it's equal to 0, then those two vectors are orthogonal. Slightly more general than that is if we had an entire set of vectors. So if S was just a whole bunch of vectors, we could talk about that entire set being orthogonal if any two of the vectors in the set are themselves orthogonal. So for all I not equal to j, we would want the inner product of the vector vi and the vector vj to be 0. Okay, so if that was the case, then the whole set would be considered orthogonal. We did a little example, I think, on Tuesday, kind of at the end of class with that. Remember that if you're checking to see if a set is orthogonal, you have to go through every possible pairing of two of those vectors, right? So in this case, you would take the inner product of v1 with v2 and make sure that that's 0. And then the inner product of v1 with v3, make sure that's 0. And then the inner product of v2 with v3, make sure that that's 0. There's a bunch of them that you would need to calculate, okay? So that's kind of the idea. Just stop me, by the way, guys, if there's any questions here as I'm kind of recapping, reviewing where we left off. But that's the idea of an orthogonal set of vectors. Now, the set is actually orthonormal, and we have to read these words carefully, by the way, because they look almost the same. And it makes a big difference because an orthonormal set of vectors is not only orthogonal, but it is also consisting of unit vectors. So every one of my vectors has to have a length or a norm of 1 in order for the set to be orthonormal. Okay, so I can give you a set of vectors. This would be a very typical question. Here's a set of vectors. Tell me, are they orthogonal? Are they orthonormal? right? They can't be orthonormal unless they're already orthogonal. So I always like to just start by checking the orthogonal property. But if they are orthogonal, then they might also be orthonormal if they have unit length. Okay. And then finally, over here, this actually I didn't write down on Tuesday, but this is an easy one, which is just that if you have a set of vectors that happens to be a basis for your vector space, of course, we've spent a lot of time thinking about what a basis is. So if you have a basis for your vector space, that basis could be orthogonal or orthonormal too, just by coincidence, depending on whether it is orthogonal or orthonormal as a set. So what I'm doing here, guys, with the parentheses is I'm just saying that I can define either phrase. So an orthogonal basis is just an orthogonal set that is also a basis. And an orthonormal basis is just an orthonormal set that is also a basis. So you're just putting two ideas together. You're putting the basis concept together with either orthogonal or orthonormal. Yeah, that's basically the idea. And again, if you have an orthogonal or an orthonormal basis, not only can every vector in the vector space be expressed in terms of that basis, right? We know that from chapter 4. A basis is a spanning set. So every vector can be written in terms of that basis. So not only is that true, but we actually have some pretty substantial computational simplicity. The calculations can be a lot easier and nicer when you have an orthogonal or an orthonormal basis in your hands. So this is really a strong property. If I have an orthogonal basis or an orthonormal basis for a vector space, I'm generally going to be pretty happy. Okay, so let's do a practice problem to kind of see how that would look in a real example. Okay, so here's a little warm up for us to try. I'm going to use the vector space P1 of R. And we're being asked here to show that if I take the vectors 1 and the square root of 3 times the quantity 2x minus 1, that is an orthonormal basis for P1 of R. That's the question. So I'm going to stop for a second and see if anybody has any issues with this question. Marco.
Just one
Question over here first. Okay.
So if it's orthogonal, does it still have an inner product space?
Yes, none of this is anything we can talk about unless we have an inner product space. So it's assuming, it's a good point, we're assuming that we have an inner product space in our hands. And if we don't have an inner product, then we can't talk about whether the vectors are orthogonal or orthonormal or anything. Make sense? I think I just answered the question so I threw a question at you, which was, does anybody have any issues with this question? Angela, do you think you know? No, that's okay. That's okay. You can actually have that's just that's not really the number one. That is the polynomial one. But that's okay. These are two polynomials in P1 of R. I don't have a problem with that. But here to tell you, I do have a problem with something with that question. Jason?
Isn't it because there are two functions that we have to do the inner problem and we don't have the A and the B?
Okay, I did not give you the inner product formula here. Remember that if you are not given the inner product formula, you can't answer the question unless it's Rn. Now remember, if the vector space is Rn, we're going to use the usual dot product unless told otherwise, right? But in this example, there was no inner product given, and so this question doesn't make sense. Like if I gave you this question on a test and it looked just like this, you would all be scratching your head saying, wait a minute, I don't know what inner product I'm supposed to use. So how am I supposed to know if my vectors are, orthogonal or orthonormal or not, right? We can't know those things unless we have this inner product to allow us to evaluate. So I'm going to add a little bit more to the question. So so let's change our little warm up slightly here. Using the inner product from F to G. And actually, Jason, it wouldn't even necessarily have to be an integral. I know that normally we think of doing the integral of f of x, g of x, dx, and that is the most common way of doing inner products using functions, but you wouldn't have to do that. It wouldn't have to be this kind of an integral, but this was certainly in the video that you guys watched, and it's by far the most common type of inner product when you're working with functions. But as Jason pointed out, I have to have limits of integration here to get a number out of it, so that has to be given to you, and I'm just going to use 0 and 1 for this for this particular example. Okay, so yeah, all of that has to be provided. If they don't give you that formula, then you kind of throw up your hands like, I don't know what I'm supposed to be doing. Yeah, Blake.
Are we, in the exam, are we going to have to like find inner products to use?
No, see, that's what I'm saying. I would have to tell you this formula, right? I started off today not giving it to you because I wanted to see if anybody was realizing that this question wasn't fully proper. So you have to be given the formula to work with. Yeah, you're not going to be dreaming these things up for yourself, right? Otherwise, everybody in the class will dream up a different one. In my grading, I will literally be in grading hell trying to figure out what everybody was doing. So yeah, I will give you the inner product formula for sure. Okay. Good enough so far? Okay, so now let's actually try to solve the problem. Okay, let's start with just trying to, so again, we're showing that we have an orthonormal basis. So let's start with just the basis part. Let's start with just the basis part. If I asked you to show that these vectors are a basis, does anybody want to give me any thoughts about that? How we could do this? Goes back to chapter 4, essentially. Audrey?
Is it already in the form, so we just pull up the X?
We're not talking about something where we're busting out variables or anything like that. Busting out the variables is like if you have ABC and you're writing down the general form. These are specific vectors. These are specific vectors. Want to know why are they a basis? Name. Li. I'm sorry. Make sure it's Li.
And that.
Yeah, so we could write this out into a matrix if we wanted to. How many vectors do I have here, by the way? Only 2. So let me ask you this. If I'm testing for Li and I only have 2 vectors, do I have to use that matrix, or is there something else that we learned about? Julie?
You could do the both or neither, and then you can use the determinant, which might help with the
both are neither thing.
orthogonal.
Okay, excellent. So we might know the dimension of our vector space and be able to compare it with how many vectors we were given. What is the dimension of P1 of R? That's 2, right? How many vectors did I give you? 2. Okay, so those numbers match. So it is, as Julia said, these vectors are both or neither. That's our coming off of our rubric that we've been studying for the last week or so. So it's both or neither based on the fact that the dimension matches the K value. Blake? Oh, okay. I'll come back to you. So I want to go back though to Nathan's point was, well, okay, so if it's both or neither, then I could test if they are Li by putting them into the columns of a matrix. And that is absolutely true. But is there another way we could do this without having to use the matrix at all? Did you come back?
If you have 2 vectors.
Yes.
If they're scalar multiples of each other, that's the only case they're linearly dependent.
Perfect. He said it perfectly. If I have only 2 vectors, right, they will be LD only if they are scalar multiples of each other. When by scalar, I mean number. So I cannot take the number 1 and multiply it by a number and create this radical 3 times 2x minus 1. So these vectors are Li. The set is Li since 1 and radical 3 of the quantity 2x minus 1 are not scalar multiples of each other. They are not scalar multiples of each other, and therefore they are Li, and therefore they are both. They are a basis, right? So that's a great way to talk through that. Again, it would not be wrong to set up the matrix, right? You could certainly do that, and you'll get no free variables, right? No free variables, which would mean Li, right? Great. So this set is both, meaning it is a basis. Okay. Right, so we have a basis on our hands. Clear enough? It's a basis. That's not the whole thing, but that's the first part. Nathan?
Would you like to put something like this, where it's not a basis? You have to check, make sure it's.
I'm not gonna throw you off and say, oh, show it's a basis, and it turns out it's not. I would have to change the problem. Okay, so we've got the basis part. Now let's get the orthonormal part. Now, of course, orthonormal requires, first of all, that the set be orthogonal. So before we do orthonormal, let's do orthogonal. So let's check orthogonal maybe right here. And to do that, I just need to make sure that when I take the inner product of the two vectors, so if you want, you can label these. This is V1 and this is V2. All right, so we've got our two vectors here. So we can just take the inner product of those vectors. So 1 and radical 3 of the quantity 2x minus 1. I'm going to take the inner product of those two vectors. And we're using the formula that they gave us here. So I have to integrate from 0 to 1 of f of x, which is just 1, times g of x, which is radical 3 of the quantity 2x minus 1 dx, like so. And if I pull out my radical 3, it's a constant, right? Then when I integrate 2x minus 1, I just get x squared minus x. And I have to evaluate that between the lower and upper limits of integration. And you can very quickly see that that is going to give you 0. Pretty easy to do the integration here. So we get 0, and so the vectors are orthogonal. So I have a basis, and it's orthogonal. The last part is I have to check that it's actually orthonormal. So guys, you have to read these. You have to read these questions very carefully. Sometimes I'll see people on a test checking orthonormal, but the question only asked for orthogonal. If I ask you to show that a set of vectors is orthogonal, then that's fine, but you don't need to do the orthonormal part in that case. So just make sure you, as I said, these words look almost the same, so it can be very easy to kind of get it mixed up. So let's check and make sure that each of these vectors is a unit vector. The norm of 1. Let's check that one out. Remember that the way we calculate a norm always, probably should have put it up here in the recap again. The norm of a vector is always the square root of the inner product of that vector with itself. So in this case, I would do the square root of the inner product of 1 with 1. And so this would be the square root of, now underneath that radical, I have an integral to do, right? So I'm going to put a 1 and a 1 for both f and g. So this is going to be the integral from 0 to 1 of 1 times 1 dx. All right, so just put the same function in both slots. Okay, so underneath that radical, when I integrate dx, I just get x. I evaluate that from 0 to 1. Pretty easy to do that. And so that's just going to give me the square root of 1, which is 1. Put a check on that. That looks like what we're expecting to get. We have the first vector is a unit vector. Okay, very computational. This is just a lot of computation. Let's check the other vector. We have to make sure that both of them are unit vectors. So let's look at the norm of radical 3 times 2x minus 1. Okay, this one's going to be a little messier, but it shouldn't be too big of a deal. So I'm going to take the square root of the inner product of radical 3 times the quantity 2x minus 1 with radical 3 times the quantity two x minus one. So I'm going to underneath the square root, make sure you don't lose the square root in all of this mayhem that's going on underneath that thing. That square root has to be there. But we're gonna calculate this thing here. I think I'm gonna actually come over here to finish it. It's gonna be a little bit of extra writing. So I'll come over to the third board here. So I have to set up an integral again inside of there, right? This is gonna be too bad, I don't think. Square root of, so I'm gonna integrate 0 to 1. And what do? Well, I just multiply these together, right? So and when I multiply them together, I'm gonna get 3 times the quantity 2x minus 1 squared dx. Okay. You can do this integral in two ways. You can either do a u substitution and let u equal 2x minus 1. Or you could just multiply it out first and then just do it term by term. Anybody have a preference? U sub. Okay, let's do u sub. So for u substitution, I would let u equal 2x minus 1. And that means that du would be 2 times dx. Okay, so underneath this radical now, we have an integral of, so keep in mind that there is no factor of 2 inside the integral, so I actually have to fix that. I have to sort of put a 2 in here, but then that requires me to divide by 2 as well. So now this part becomes du, but I have now 3/2 of u squared du. Oh, it's good refresher from calculus. Don't forget that when you do this, you also have to change the limits of integration. So if x was going from 0 to 1, now u will be going from -1 to 1. So we have to get those limits correct. And so we have new limits of integration. I'll pull the 3/2 out. When I integrate u squared, I get u cubed over 3. I'm going to evaluate that from -1 to 1. And so let's take a look. This is just going to be the square root of 1/2 u cubed from -1 to 1. And I think that's going to be 1/2 minus -1/2, which is actually 1. So this is what you were hoping to get. We got a 1 out of that. So this is a really good warm-up problem. Probably put something just like it on the test, right? Very good question. So I give you a set of vectors. I ask you, show me that it's an orthonormal set, an orthonormal basis. So you first show that it's a basis, then you check that it's orthogonal, and then you check that it's orthonormal. So yeah, if you just came in, you may want to take a picture of the board before I erase it, but that's a nice problem that involves a lot of little pieces. What do you guys think? Any questions on that? You okay with that? Yeah. It's a little bit of integration here that you have to deal with. Is that a hand up? Yeah, Blake, go ahead. Yeah, so if x is 0, then when I plug 0 in right here into this change of variables, it'll give me the corresponding u value. So u would be -1. And then when x is 1, which is the upper limit, if I plug in 1 there, I get u equals 1 as well. That's how you do it. Actually, when I teach calculus, which seems like almost never these days, since they always have me teaching this class, but when I teach calculus, I will sometimes tell people that you could just drop the limits of integration while you're doing the u substitution. And then once you get the antiderivative, you can turn it back in terms of x again, and then stick with the original limits. It's whatever your personal preference is. I don't want to get too bogged up in that part because that's just the calculus of it. But yeah, so that is a nice little problem about orthonormal basis. Okay, you might wonder, where did we come up with this basis? After all, to me, the easiest basis for P1 of R would have been 1 and x. That would be the basis if somebody, challenged me to find a basis for P1 of R, I probably would have said that. It's so much easier. Where does this radical 3 and 2x minus 1 come from? That's a legitimate question. How do you come up with a basis that's going to be orthogonal or orthonormal? So I'd like to talk about that. kind of the next thing I want to do today is just kind of go over that a little bit. Let me get this cleaned off and we'll do it. So I guess the question, we'll phrase it maybe as a question, maybe sounds like the best way to do it. I'm gonna phrase this as a question, guys. The question is going to be, given a basis for some vector space V, how can we refine it to be an orthogonal or orthonormal? I don't know, it just depends which one you want to have. An orthogonal or an orthonormal basis. While we're thinking about it, another good question would be is why do you care? Why not just live with this basis for P1 of R? Why in the world would you want to go to something that looks on the surface to be more complicated? Right? Why would you choose to do that? So there are nice properties that you benefit from when you have a set of vectors that are either orthogonal and or orthonormal. Computational simplicity comes to mind. Calculations can be much easier using the inner product when the vectors that you're focused on are already orthogonal. It just makes life easier. The calculations, the computations up using that inner product are much easier if you have an orthogonal or an orthonormal basis. That's why you would want to be able to do this. Okay, so you might have a basis for V, which is an inner product space, and you would like to replace it with a better basis, right? A basis that's actually orthogonal or orthonormal. And that's what the heart of this question is all about. I'm going to show you a little diagram of this to help you kind of visualize this. And I have to warn you that this is a little bit different notation than what's in the book. I'm kind of going to this last section here now on chapter 5 to talk about this. The idea is we start off with a set here, V1. This is just a little diagram that I'm going to draw. Make sure you give yourself plenty of room here to draw this little picture. So I'm going to start off with this set here, and I'm just going to assume that this is a basis for V. So I have some vector space and I have a basis for it. Okay. What I would like to do is some process that I'll explain shortly. I would like to replace it with a new basis for V, which is going to be W1 through Wn. And this is actually going to be an orthogonal basis for V. An orthogonal basis for V. So I'm going to basically trade out the original basis vectors, V1 through Vn. I'm going to trade those out for a better basis where the vectors are themselves orthogonal, right? The inner product of any two of them is 0. I have to explain how this is done, which I will shortly.
Does that mean that since you have B and W, does that mean that the number of vectors will stay the same?
It would have to, right? Because after all, there's a dimension for this vector space that doesn't change. It's n. And so if it took n vectors to form a basis for V in the first place, then any other basis for V that we might modify our set to is also going to have n vectors. The number of vectors in the set will not change. That's a good question. Maybe orthogonal, having an orthogonal basis is good enough for the purposes of whatever you're doing, but it is also reasonable to ask whether we could take it even one step further and replace this orthogonal basis with an orthonormal one. So I'm going to make another list of vectors, still n of them here, u1 and u2 and so on up to un. And this one, I want to imagine that this is an orthonormal basis for V. Okay, so this is kind of the picture I want you to have in your mind in connection with this question. So given any basis for V, we would like to think about how to refine it to an orthogonal or an orthonormal one. I actually want to start with this part of the diagram first, the part on the right. If I had a bunch of vectors that were already orthogonal, but they weren't yet orthonormal, meaning that they weren't yet unit vectors, would there be a way of trading those W's for the U's here so that we could convert from an orthogonal set to an orthonormal one?
Yeah.
I would only ask this if I had explained it somewhere. If you watched my video, Taylor?
I'd say if it isn't one, that you would times the entire set by whatever the remainder was. Or one over the.
What you're doing with your hands is exactly right.
Sorry.
Yeah, no, you basically take the vector and you normalize it, right? You divide by its norm and that shrinks it down into a unit vector. So if I have a vector, you know, W, if I have a vector W here, then I can shrink that down so that it's just a unit vector by dividing by its length, right? That's how you shrink that down. So this is a process that I talked about in the video that you guys watched over the weekend. What we can do is what I'll call normalization. So for this step, we would do normalization. And the way that normalization works is, again, very familiar. You probably even did this in Calc 3, right? Where basically what you're going to do is you're going to get the use of I vector by just taking 1 over the norm of Wi and then multiplying it by Wi. So this is the standard way of replacing a vector with a unit vector. It doesn't change the direction. It doesn't do anything other than shrink the length of that vector down so that it has a length of 1. Okay. Does that all look familiar? Right? So if you have an if you have an orthogonal set, right, guys? So if you have an orthogonal set in your hands already, it's easy enough to orthonormalize it. You just divide each vector 1 by 1 by whatever the norm of that vector is, and that will normalize your set and give you an orthonormal set of vectors. Okay, so now we have to talk about, is everybody okay with that? Any questions so far? Now I have to talk about the left side of the diagram, which is the more interesting part. That's sort of the new part that probably we haven't seen before. Which is, how do I start with a random set of vectors and get them to become orthogonal? Like, how do I replace the V's with the W's in the first place? So this is a new thing. I'll put a little arrow here to describe this one too. There's a name for this process. And this is called the Gram-Schmidt process. It is based off of, well, the name comes from 2 mathematicians who sort of independently discovered how this could be done using an inner product space. So I have to describe this process. This takes slightly more effort to explain it. So I'm going to come over to this other board to explain the process. So you could just say, here are your notes. You could just say see below. We're going to explain it here below on this next board here. Okay, so here's the idea. Let me just imagine, I'm going to actually draw a picture of this. Well, actually, before I draw the picture, I will tell you first of all that W1, what you're going to do here, guys, is you're going to let W1 is just going to be the original V1. So you don't make any changes to the first vector. Whatever the first vector is, just stays the same. So, but then here's the issue. So you maybe you had V1 right here and you had V2 right here. And as you can see, the way I drew them, they are not orthogonal right now. They are not at a 90-degree angle. But what we are going to do, my friends, is we are going to, well, first of all, we're going to relabel V1 as W1. Okay, so remember, W1 is just going to be V1. And what we are going to do is we are going to do a projection of V2 onto V1. So I'm going to draw a perpendicular line here, a dotted line here. I'm going to make this a perpendicular. And this vector right here, that is sort of the part of V2 that is pointing along W1, right? This is called the projection of V2 along W1. So we write it like this, P of V2 comma W1. And again, the way I would call that is this is just the projection vector of V2 along W1. That is what's called a projection vector right there, the projection vector. But what we're going to actually do, guys, is we're going to create a vector. I will draw this one in red. I'm going to draw this vector here, which is perpendicular to W1. And in fact, this red vector is going to be the W2. Okay, so notice that the blue vector plus the red vector adds up to my original V2. And what I'm going to do is I'm going to solve for what W2 is right now. W2 is V2 minus the projection of V2 along W1. So, am I color coding it correctly? I'm trying to. So this just literally vector addition here. The blue vector plus the red vector equals the black vector on that triangle. And it is a right triangle. It is a perfectly good right triangle. So I'm just literally solving for W2 in that notation. Now, that's going to end up being my second vector over here. And you can see from the picture that W2 is orthogonal to W1. Because W2 is going this way, W1 is going that way. There's a 90-degree angle right there. But I don't want to leave the formula like this. This is not so nice. Let's actually see if we can figure out what the projection vector is. Okay, you guys want to help me with this? So I'm going to keep the V2 here. But I would like to figure out if we can rewrite the projection vector in a nicer way. To help me do that, it might be good to label this angle theta here that is sitting between the original two vectors that are in black. Because I think everybody knows, right? Everybody knows that the length of that blue vector would simply be, I'm just thinking about trigonometry here. We would take the length of the black vector and hit it with the cosine of theta. Right? That's exactly what it would be. So the length of this vector, okay, I'm not talking about the vector itself yet, but the length of that vector is simply the norm of V2 times the cosine of theta. That's the length. That's just a number. So far what's on the board doesn't make any sense. I have a vector minus a number. But I'm going to fix that because what I'm going to do, guys, is I'm going to make a unit vector right here. I'm going to make a unit vector that points along W1. And then I'm going to use this as my stretch factor. That's the scalar that stretches it out to be exactly the correct length. How do I make a unit vector that points along W1? I just do it like normalization. So I literally just have to take W1 and divide it by its norm. That creates a unit vector that is pointing this way. And then what am I doing with that unit vector? I'm stretching it out to be exactly as long as the projection vector is supposed to be. And that is the blue vector in the picture now. So this is also a good formula for the projection vector. But I'm going to go even a step further, guys. We're going to go even a little further with this. And that's because we actually had a formula for the cosine of theta the other day. You probably remember it. Let's see if we can write it down. There is a formula here for cosine of theta. Let's see. It was the inner product of the two vectors. In this case, the two vectors are V2 and W1. Divided by the norm of V2 and the norm of W1, right? This is our cosine of theta formula. And then we'll have the vector W1 divided by the norm of W1. Okay. I'm gonna end up with a very nice formula in just a minute here. Okay, so this is still equal to the black vector V2 minus. What you'll hopefully notice, guys, is that we can cancel the norm of V2 from the top and from the bottom there. And so what is left is, well, there's some big scalar in front of W1. So the W1 vector is over there on the right, but then what's the number that goes in here? I'm gonna put it right into this little spot right here. The inner product of V2 with W1 on top. And notice that there are 2 powers of norm of W1 on the bottom. There's 2 of them. So I'm going to square that. And that is the formula for W2. Okay, so that is the answer that we're looking for. So let's just write it down now fully in black so that we can all see it super easily. I know not everybody has colored pens with them all the time, so we'll just do it in a black marker here. That is the formula for W2. And that will be orthogonal to W1. Remember, the goal here is to create an orthogonal set of vectors. So I replace V1 with W1, but that's really nothing. Just it's the same vector. But I'm now going to replace V2 with W2, which is obtained by taking V2 and subtracting the part of V2 that was kind of parallel to W1. We don't want that. We want to make we want to make W2 perpendicular to W1. Okay. So that's kind of the first step in this Gram-Schmidt process. So you actually don't need the theta. Notice that theta is not in our final formula at all. You just have to be able to take inner products. Okay, and I'm just going to say here, guys, similarly, we can do W3. I won't go through the whole geometric derivation again, but I'm just going to write down the formula now for W3 as well. And so I'll come over here to do that. W3 is going to be V3 minus, this time we have to subtract projections along both of the first 2 vectors. So there will be a term here where we take the inner product of V3 with W1 divided by the norm of W1 squared times W1. Makes sense. That projects V3 onto W1, but then we also end up having to subtract the inner product of V3 with W2 divided by the norm of W2 squared times W2 this time. So this is the formula for W3. That's the formula for W3. So I've got, maybe I should put this one in a box as well, right? So I've got W1 is just V1. Here's W2. Here's W3. And you can imagine that this could go on endlessly all the way up till we get to n vectors. I won't write down any more of the formulas. Instead, what I'll do is just give you guys a little bit of good news here, or just give you a little peace of mind. I will never ask you to do the Gram-Schmidt process for more than 3 vectors. So I've given you as much of the process as you'll do, because if you go to if you go to a 4th or a 5th vector, it's just messy. It's not really conceptually very interesting. So I would stick with just 3 vectors at the most. The other thing is, on your exam a week and a half from now, I am going to give you those W formulas. You do not need to memorize these formulas in the box. The biggest thing you need to be able to do is you need to recognize, when am I supposed to do the Gram-Schmidt process? That's, if anything, where people get tripped up. Right? There's a question and they're like, I don't know how to do this problem. So how do you recognize that you're supposed to do the Gram-Schmidt process? Let's just remember the big picture diagram here. This is actually what I really want people to appreciate. What it is if I would like to have an orthogonal basis or an orthonormal basis, right? Those are the situations when, so if the question is asking you, find an orthogonal basis for blah, 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 or an orthonormal basis for blah, blah, blah. That is a tip-off that you should use the Gram-Schmidt process, and I'll give you these formulas. If you write Gram-Schmidt on your paper, I'll give you credit for knowing that, and I'll be really happy about it. So it's actually, this is not that bad. It's not that bad. It's all computational. Let's do an example just to see the Gram-Schmidt process in action here. And then this is the last thing for chapter 5, by the way. So I know we feel like we just started this chapter, but we're gonna close it down pretty fast as well. Okay. Questions? Let's try an example. Okay, so let's do this example. Find an orthogonal basis for S, which is going to be the span of the vector -1, 1, 1, 1. And then my second vector is going to be the vector 1, 2, 1, 2. Okay. We'll take this example here. So I have two vectors. I would recommend that we label them. So the first one, I'll call it V1, and the second one, I'll call it V2. By the way, what universe are these vectors living in? R4, right? It's 4 dimensions because there's 4 slots there. Since it's R4, notice that nobody told us what the inner product was that we're supposed to be using. So, but because it's Rn, we have slots here, we can assume that we're going to use the standard inner product, right? So the dot product in this case. So I'm just going to use a regular dot when I start doing these formulas, right? I'm going to just be doing regular dot products. Okay? And these vectors are already a basis for S. They're not an orthogonal basis yet, but they are a basis for S. Does somebody want to explain to me why that is? Why do I know these are a basis for S? Yes.
Know there's, and then they're.
Beautiful. In case anybody didn't quite catch that, these vectors already span S because S is created as the span of those vectors. So these are a spanning set for whatever it is that they span. And they are not scalar multiples of each other. There's only 2 of them, right? 2 vectors that are not scalar multiples of each other are always Li. So these vectors are Li and they are a spanning set. So maybe before we actually solve the problem, I'm going to note that V1 and V2 is a basis for S. It's not orthogonal yet, but it is a basis for S. I'm pretty comfortable with that. Okay. So whenever you see problems like this, where the vector space is the span of something, the vectors that are in the list, they are already a spanning set for that. It's just a question of whether they're Li or not. In this case, they are Li by inspection simply because they're not scalar multiples of each other. I can't take one of these vectors and multiply it by a constant to get the other. So these are Li, and so therefore they're a basis. Okay, great. So, but let's work on the orthogonal basis part. So for the solution now I'll jump into the Gram-Schmidt process. Let's just put that here. I'm going to use this process that we just described a moment ago. So the first step is to write down W1. W1 is just V1. And so it's just the first vector, -1, 1, 1, 1. Okay, so there's your first vector in your orthogonal basis. And then secondly, I have to do the second vector W2. And I've got the formula for it over there. It's V2, which is 1, 2, 1, 2. That's V2 minus. And then guys, there's this fraction here that we're going to fill out the numerator and denominator of in just a moment. And that will be multiplied by W1. Let me just put down W1 here, -1, 1, 1, 1. Okay. So the only thing I really need to figure out carefully right now is the numerator and denominator of this fraction. The numerator is just the inner product of the second vector with the first vector, right? Actually, it's literally just the inner product of these two vectors. Okay, because this is V2 and this is W1. So you literally are just going to dot these together. So what am I gonna get? -1 plus 2 plus 1 plus 2, right? Just regular dot product on that. -1 plus 2 plus 1 plus 2, that comes out to what? 4. Everybody awake this morning? I know, sorry, just making sure everybody's awake. Great, so that's a 4. What about the denominator? The denominator is the square of the norm of W1. So just to remember how that works, remember guys that the norm of a vector is the square root of the inner product of the vector with itself. So if I square both sides of this, if I wanted to know what the square of a norm was, well, I can do that by just dotting the vector with itself. Okay, so just get rid of the radical and you have that. So I just have to dot this vector with itself. -1 times -1 plus 1 times 1 plus 1 times 1 plus 1 times 1. That's 1 plus 1 plus 1 plus 1, which is 4. It's also 4. Okay. So again, if you need a little help for your notes here, this is just, the numerator here is just the inner product of V2 with W1. And the denominator right here is just the norm of W1 squared. That's just coming from that formula in the box there. Okay, and so we can, we can cancel the 4s. And so all we have to really do is just subtract the two vectors. So it's just the second vector minus the first vector. So, yeah, second vector minus the first vector. So 1 minus -1 is 2. 2 minus 1 is 1. 1 minus 1 is 0, and 2 minus 1 is 1. So it'd be 2, 1, 0, 1. Slot by slot subtraction. Okay, and so my final answer, I think I'm going to put it over here, guys. My final answer for my orthogonal basis would be the set with -1, 1, 1, 1. And then the second vector is 2, 1, 0, 1. Like so. That's the answer. In case you're a skeptic, you can double check that they are orthogonal. Just do the dot product of them. These should be orthogonal now. So if I dot them together, -2 plus 1 plus 0 plus 1. That adds up to 0. So that's an orthogonal set. These vectors will span the same S that the original vectors did. But now they are orthogonal. They are somehow better than the set we had before. Okay? Gilbert, go ahead.
In the answer, why do we keep V1 not?
This is W1. I want you to think of this not as the V's. These are the new orthogonal vectors, the W1 and the W2. It just happens that W1, the first vector is always going to be the same as what you had in the original set. It's only the later vectors that are going to change with the formulas.
Thank you.
Good question. Yeah, great. Anything else about that one? Let's do one more example and then we'll take a break, okay? And then we'll be done with chapter 5 too. So let's try one more. All right, so let's do this example. Let's find an orthogonal basis for S, which is going to be the span of 1 x squared and x to the 4th. So I've got to give myself a little bit of room here, but I'm going to try to keep the boxed formulas up on the board because we're probably going to want to use those again. Incidentally, guys, before I go on, I kind of forgot to say something over here. If this question had asked for an orthonormal basis, again, read the questions carefully. If it had asked you for an orthonormal basis, then what you would need to be doing, of course, is taking these W's and dividing by their norms. So that's the normalization process. The norm of W1 is actually just 2. So you would divide by 2 here. the norm of W2 is just radical 6. You would divide by radical 6. So if I ask you, you know, you don't need to make a big deal in your notes about that, but if the question was asking for on a normal basis, you would have needed to do that at the end. When I first was looking at this subject years and years ago, I was having people normalize their vectors as they go along. So, you know, you can say, well, I'll start with W1 and I'm going to normalize it right away, and then work with that to do the W2. It's not a good idea. I figured this out the hard way, because what happens is a lot of times you'll get things like radicals into your slots of your vector right off the get-go. And then all these calculations become, of course, much more tedious to do. So it's better to not normalize your vectors until the very end, after you have the orthogonal set. It's not that it's wrong to do it as you go along, but it's just messy to do it as you go along. So anyway, on this problem, we're not going to do the normalization either. I just want to find an orthogonal basis. Let's label the vectors v1, v2, and v3. And I guess before I go any further, I would like somebody to tell me why this is a flawed problem the way it is currently stated. Marco.
Is it because it's a scaling?
No, nothing wrong with the vectors themselves. Eduardo?
Are we like not given the that formula?
Yeah, we don't have the inner product that we're supposed to be working with here. And if they don't give you the inner product, then you're not going to know how to do these calculations here, right? If you don't have that inner product formula. So this is a flawed question. Let's fix it. Okay, so I'm going to say here, let's use the inner product of f with g. We're pretty familiar with the integration, so we're going to integrate f of x times g of x dx. This time, let's use limits of integration from -1 to 1. Okay, so I'm going to assume that to begin with. And we are now going to start solving the problem. Once we have the inner product, we can start solving it. Okay, so for the solution, W1, of course, is just V1, which is just 1. So I'm already done with the first vector. Okay, W1 is just whatever V1 was. Okay, so now I'm going to work on W2. For W2, I have to take V2, which is x squared, and I have to subtract. Give yourself plenty of room here, guys. In this parentheses, I'm going to make a fraction, and I have to subtract some multiple of W1. W1 is just 1. Okay, so what goes on the top and on the bottom here? Well, you see the formula. On the top, I have to take the inner product. The inner product is going to be an integral. So I'm going to have an integral from -1 to 1 of V2 with W1, right? So V2 times W1 is just x squared. Dx, okay, that's going to be on top. And then on the bottom, I have the square of the norm of W1. So that's just the inner product of W1 with itself. So we'll be integrating -1 to 1 of 1 times 1 dx. Okay, so that's setting it up. Both the numerator and the denominator involve the inner product. And so that's why we see the integrals coming from the given inner product formula here. So this is x squared minus, now let's just work out the fraction. I'm going to do this kind of quickly because it's not a very hard integration to do. When I integrate x squared, I just get 1/3 of x cubed. But when I evaluate that from -1 to 1, I think I should get 2/3. Should be 2/3 on top. And then on the bottom, when I integrate dx from -1 to 1, that should just be 2. And then this is times 1 on the end of that. Okay, so this is actually just x squared minus 1/3. That is my W2 vector. X squared minus 1/3, just simplifying the fraction there. Okay? That look okay to everybody? Trying not to go too fast, but the integrals are not hard. Relatively easy calculation. if we're good, this problem has a third vector, so we actually have to use the W3 formula. I think I'll actually try to write it directly below the W3 formula here. So the W3 is going to be V3, which was x to the fourth. From that, I have to subtract some fraction that I'm going to fill in a minute times W1, which is 1. And then minus another fraction that I'll fill in a minute times W2. W2 we now know is x squared minus 1/3. Okay, so it's just a matter of putting the numerators and denominators in from the formulas directly above. Okay, this is pretty cookbook process here. Nothing, you don't have to think too hard, just have to plug things into the formulas in the right place. So in the numerator, I'm going to take the inner product of V3 with W1. That's x to the fourth. So I'm going to integrate minus 1 to 1 of x to the fourth dx. Okay. And then in the denominator, I'm going to take the inner product of W1 with itself, guys. So please remember, always remember that when you square a norm of a vector, it is literally just means that you're taking the inner product of the vector with itself. So that's exactly what I'm going to do on the bottom. That'll be an integral from minus 1 to 1 of 1 times 1 dx. So I'll have all of that. And then this term is also an integral. This is the integral from minus 1 to 1. Inner product of V3 with W2. So that's actually integrating. V3 is x to the fourth. W2 is x squared minus 1/3. So that's actually going to be integrating x to the sixth minus 1/3 of x to the fourth dx. That's on top. And then on the bottom, we have to integrate minus 1 to 1 of the inner product of W2 with itself. So that would just be x squared minus 1/3 squared. Okay, so it looks kind of messy, guys, but all of these things are just integrals. They're just integrals that you have to calculate. So let's just clean this up quickly here. This is x to the fourth minus this fraction here. Let's just see. When you integrate x to the fourth, you'll get 1/5 of x to the fifth. Then when you evaluate at the limits, it's going to give you 2/5. The denominator is, again, 2. We already worked that one out. That's multiplied by 1. And then minus, we have another fraction here, times the quantity x squared minus 1/3. And I am going to not spend the time on working out these antiderivatives and plugging in the limits. I'm just going to tell you what the answers are. So you can check these if you want to. The numbers get a little bit messier. So 16 over 105 on top, and then 8 over 45 ends up on the bottom here. So you can check those are the antiderivatives. And then we've evaluated them all from -1 to 1. Okay, so I'll let you check that part. This can be cleaned up a little bit. And again, I'll just have you check the algebra here. It's nothing too interesting. You're going to end up with an x to the fourth. And then there's also going to be an x squared term, which this coefficient actually reduces down pretty nicely to 6 over 7. So this is going to be 6 over 7 times x squared. You can check that. And then we have a constant term, which is going to be, again, I'll have you check this, 8 over 15. And that has a minus sign on it. So this is just cleaning the whole thing up. This would be the W3. Okay, so my final answer here would be the first vector is 1. The second vector is x squared minus 1/3, which is in the box over there on the right side of the middle board. And then this is my third vector, assuming I did all my integrals correctly. This is my third vector right here, okay? And if I really wanted to torture my students, I would ask them to give me an orthonormal basis for this span, which, as you could imagine, would be horrendous because now you have to normalize these. That's not as easy as it looks, right? The integrals are going to be a little nasty on that. So, but we're not going to do that. What do you think, guys? we can replace any basis with an orthogonal basis. Notice, when you think about what the span of these vectors is, it's just things of the form, ax to the fourth plus bx squared plus c. And take a look at the form of all of these basis vectors. I only see even powers of x. I don't see any x cubed or x. It's just x to the fourth, x squared, and constants. It's exactly what we would expect. Audrey? Yeah.
Basically taking the product of, W itself.
Yes.
So that's why you use the integral, because the formula for the inner product.
The formula for the inner product is an integral. Yes, exactly, exactly. So that's why you have to go through all of that. Good point. Excellent. Comments, questions? This is tedious a little bit because of all the radicals that show up, but there's conceptually not a lot here. This is a section students usually do pretty well with, because if you know how to do W2 and W3, and I've already promised you I won't give you more than that, you can run through these calculations without too much struggle. So that's the whole story. Let's take a break until about 11:20 or so. During the break, if you have other questions that you want to look at from today's homework assignment, feel free to write them on the board. I am going to save some time for that here at the end. So, but we'll take a break, give you guys a chance to decompress. It's in the homework. Yep, you'll get a chance to practice that. Good.
No, it's the same, so. Unless it's. Oh, you really would not have a white room. Think that you're.
You're not welcome.
But I know I.
Which for minutes no, it's like introduction, you always make sure the quiz on that one, like, I was saying, one of the surgeons. Like. I just know the building. Well, there's a last one, but there's still the last. I'll just have a cool one, I'll say somebody. I don't really sure water, it's pushing. Were you? Yeah. But that's because. Someone kind of told me, because I was 7, and then I'm like, I know if I'm going to be on it. Well, if you have time, you as well. Whatever. lines have. Yeah, no, lines have, if you have a restaurant, and if you don't have something, if you have like things you wanna go to, where you get a little short lines, and then we come out of it, we don't mind if they're not in one. I just go to the ones with them, and then they don't listen. Try to go to the diamond spot, I did. You went full, I would play every single one, I was with one. It's okay. Did you say, open, ready, I'm not doing it right, I didn't. Yeah, that's, I was like, okay, it was. You could go anywhere, it was such a big full. Some care a lot. They specifically put me to it. They didn't like. Fun place. What made me sick was like, I'm so bad at thinking. Others still hurt me or insanely. I'm not the name of it really depends on the things you have. I remember those when I was, it was one of the physics reading. And there was like no symbol. And then just this was like. Okay, let's see who's going to. You're free. That's what I'm saying before I say things. It was so important.
Yeah, I saw the implied medical. Oh, you should.
They'll get you to be able to be.
I was like, what I like about the live is like, this is a big exam.
On your list, it's like. Don't go. Next year.
I'll probably. You don't want to. I'll probably say it's more.
That's a good thing. Eric's still working.
I saw.
You went to.
No, you went to it.
But I do love to go.
I can't go above LA. I'm like, I can't. I drive to LA, but I wouldn't drive above LA.
Every. Then we have to drive getting this on the. Oh, yeah, for the whole summer. Yeah. Or you could get like a time machine. I never mind. You could rent like an RV or something. You could get a tent with.
I have done. I wanna go on top of that mountain. I think go in here or.
I have 10
Then I'll do.
I know it. My voice is so good. I don't even sound.
Some other way to avoid the.
What are you wearing? I'm wearing a black blazer, yeah. And it's gonna be. Yeah, I'm buttoning my blazer. I'm wearing like a maroon blazer, fancy, black pants, like nice pants, and then like a black kind of fitted shirt because it's what I have, and then loafers,
I'm not watching.
but like fancy loafers. But like cute ones. With like a little buckle thing. Imagine. Oh my god. Like, it just Crocs on the bottom. The platform Crocs are just
With
regular.
ending regular and different.
Okay, that would be kind of.
Like a construction hat.
I would hire on the. What the Marine Corps is gonna be there. And they're gonna be like.
Oh, should have brought some crayons.
Like my favorite form. These are the Marines.
Yes.
Gather us back up again. Wow, lively, energetic folks in here this morning. That's good to see. I hope that the math is perking you up a little bit. If that's possible. I don't know. For me, it always does the charm. But yeah, anyway. I'm gonna pick things back up here again. This last half hour, I'm mostly planning to kind of go over these some of these homework problems that are on the board. I've actually put the last sort of towards the end of the assignment up here first. I think I'll start with these. So this is on the homework that's due tonight. And I should also mention because I moved the exam back, I also shifted the due dates on the homework a little bit. So this one is still due tonight, but there won't be anything due over the weekend. The next assignment will be due on Tuesday, and it's going to cover the Graham-Schmidt process basically, and orthogonal or the normal sets and stuff. So you'll have some time to work on that. But in the meantime, let's try to get this assignment done for today. Couple of problems here. 31 just asks us to derive a formula for the inner product of u plus v with w plus x, just very abstractly, okay? And so this is a quick little exercise where let's just start with what we're given here, u plus v. I'm going to take the inner product with w plus x. And the idea behind this, behind both of these problems actually, is to use the axioms, right? Use the axioms of a vector space to expand this out. So you might remember it was, I guess, axiom D is the one that allows you to split up the plus sign in the first slot. So you can actually break this down as u inner product with w plus x, and then plus the inner product of v, again with w plus x. So we can start off by just splitting up the first slot. Now, technically there is no axiom for splitting up the plus sign in the second slot. That's not from the original list. So there's two ways you could go from here. One way would be you could say, well, there's no axiom for it, but Dr. Annan did it in his video. And in the video that you watched last weekend, I showed as an additional property that you can also split up plus signs in the second slot. That's one way to do it. Let's say you don't want to use my video for that and you want to stick strictly to the axioms. What you could do, and I think I'll do it this way just to kind of be very self-contained about my explanation. You can use the axiom B, which allows you to switch the order of the two slots. So I could put the w plus x first and then inner product that with u. And then I might do the same thing with the second vector here, w plus x, inner product with v. So just you could switch the order of them. And then because now the plus sign is back in the first slot again, now you can use the axiom D again to split that one up. So this could be broken up as the inner product of w with u plus the inner product of x with u plus the inner product of w with v. Just a little more room here. And then plus the inner product of x with v. So now you've got it totally broken down. Just as a final step here to switch it back, you don't really need to, like you could just say that's the answer. And that would be fine, but I like to get everything back in the same order that it was given to me. So I'm gonna switch each of these back again. So the first one would be the inner product of U with W. The second one would be the inner product of U with X. Third one is the inner product of V with W. And the last one is the inner product of V with X. So I'm just switching, I'm using axioms B and D only to do all of this work. But essentially, if you go back to where we started from and where we've ended up, it's literally almost like you're foiling the expression, right? It's almost like you're taking this thing and you're doing FOIL. This times this, and then this times this, and then this times this, and then this times this. There's 4 terms. And so that's what ends up happening. Yeah. That look okay to everybody? Okay. So, and you can use this going forward. We can use this anytime we see, something plus something, inner product is something plus something. We can use what we just derived right here in problem 31. In fact, I think we might even want to use it on 36. So I'm gonna talk about this one now. This is another, by the way, the way I've structured this is, I'm pretty picky about this. Notice on the left side over here, you should have nothing but white space. Your whole calculation happens on the right-hand column. And what the mistake is I see sometimes with people doing on this kind of thing is they'll be like manipulating both sides at the same time. And they'll get to the bottom and they'll have like 0 = 0 or something. And I'm like, yeah, 0 = 0. I knew that when I was 4 years old. That's not telling me anything new. So you don't want to be deriving something like that. It should literally be, if you're proving that one thing equals another thing, try to do it as a chain of statements vertically down your paper. Also, I'm a stickler about equal signs. This shouldn't just be chicken scratch calculations that are not connected to each other. You need to use equal signs to kind of connect from one step to the next everywhere you go along. It's just a little more, I don't expect this to be like professional, super high quality, but it needs to be readable and logical. So this would be a great way to format that. So let's try to do that here. So let's not start manipulating on both sides, because that's going to be very confusing, and it's something at the bottom of the board. It's going to be just like a tautology. Something's just obviously true. Let's just start with the left side here. So the norm of V plus W squared minus the norm of V minus W squared. I just start only with that. And I'm going to try to get to the right side. Okay, so I don't know what this is equal to yet. I'm just going to start working on it. Okay. So this is the square of the norm. So I think we've been talking quite a bit about this today. That's literally just the inner product of the vector with itself. Notice that there's no radical on that because we've squared it. Okay. So inner product of V plus W with V plus W, and then I've got minus the inner product, same thing, inner product of V minus W with V minus W. So there's just a similar term there. Again, I've been very careful to have my equal sign here. And now I'm only going to write over on this side. So no writing is allowed over here. We don't want to see anything on this side. We're only going to connect steps on the right side using these equal signs. And we're going to trust, hopefully, that we get to this 4 times the inner product of V with W. Well, you see with this expression, you can actually just use the formula that we just derived here, which basically just says that you're going to FOIL it out. So when I FOIL this out, I would get the inner product of V with V plus the inner product of V with W plus the inner product of W with V, and then plus the inner product of W with W. That, all of that is just the first part. So I have more still to do. I have to subtract. I'm going to use brackets on this. I'm going to subtract this guy. And for this guy, I also will FOIL it out into 4 terms, right? So I'll get the inner product of V with V again, and then minus the inner product of V with W, and then minus the inner product of W with V, and then plus the inner product of W with W. So I have all of that. Okay. So a couple of those terms have minus signs on them, so we've got to be a little cautious with that. And let's see what we can cancel here, because there's a lot of things that look similar in this expression. So I've got, the inner product of v with itself, and then later I have minus that, same thing. I could cancel those. And I actually have the same thing with the inner product of w with itself. So the WW term has a minus, right? This is minus on this WW term. That also cancels. Okay. Then I've got minus negatives here. So effectively, these two things are being added because it's being subtracted with a negative in front of it. So it's actually plus, 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 and plus. 4 things added together. What are these 4 things? Inner product of v with w, inner product of w with v, inner product of v with w, and inner product of w with v. We want to add all of those up. What's that going to give us? 4 copies of this. Remember that the inner product of w with v is the same as the inner product of v with w. So this is the same as this, which is the same as this, which is the same as this. It's just 4 of the same thing. We're done. We're already done. We're already done. just that easy. Are we good on that? Checklist over here. So that's 30. Oh, and there is a part B on 36. So be sure to try that one. It works just like this. It's almost the same thing, but that would be a great one for you to practice on for the homework. Okay. So I won't do part B. I'll let you guys try part B later today if you have a chance. Now we get to the truth of the matter, which is that both of these 2 problems that somebody wrote down over here were in the video, already done. So if you go back to the video that you watched last weekend, you should have notes on that. Those problems were already done before you previously. So I'm not going to do them again. I'll let you watch the video for that. The only, yes.
I'm sorry, I wrote down 31, but I meant 32.
Oh, you meant 32.
I'm
Oh,
sorry.
oh, okay. Well,
Plenty of time to be.
okay, I want to look at number 4 first, so I'll come back to that. Yeah, so anyway, guys, check out the video notes for 17 and number 8. And if you still are shaky on it, of course, I'm happy to talk more about it, but I'd rather do something more interesting in the meantime here. Okay, so number 4, kind of hesitating about it because it's not really that. It's the reason that number 4 is probably on the board is just because there's some nasty integration that you have to do here. So you're going to work with this calculus function inner product again, and I think the limits of integration on this one are going to be 0 to pi over 2. So this is given on problem 4 essentially. The inner product of 2 functions is the integral from 0 to pi over 2 of f of x and g of x. And it's just asking you to find the angle theta between, so f of x is, what is it here? Sine of x. And g of x is cosine of x plus 2 times cosine of x plus 4. So those are the functions that you're being asked for. So just to remind you, again, we've had some chance to practice this already, but the cosine of the angle, this is just coming from the formula, the inner product of f with g divided by the norm of f and the norm of g. Okay, so we have to calculate all of those things. Get this over here. Right, so this is problem 4, and it's a purely computational problem, right, that involves that integral. So it's just a little bit of work in terms of calculation, but the concept is not bad. So for the inner product of f and g, we're going to integrate from 0 to pi over 2. Now I have to put in the functions. So we have sine of x, and then we have 2 cosine of x plus 4, and then a dx on that. And before we actually integrate that, I think it might benefit us to kind of expand this out a little bit. If you take 2 sine x cosine x, well, let's just put that all together. 2 sine x cosine x, and then plus 4 sine x. So just kind of make a expanded integral there, expand that integrand a little bit. And I am gonna do this fairly quickly. I don't want to turn this into too much of a just integration session, but I would do the first integral by u substitution. If u is equal to the sine of x, then the du is cosine of x. So this is 2u du. You integrate that, you just get u squared. So that's just gonna be sine of x squared, right? And then the antiderivative of sine of x, as you guys know, is negative of cosine of x. So that becomes, with the 4 in front of it, minus 4 cosine of x. This now has to be evaluated from 0 to pi over 2. Right. So I have to work out these limits. When I plug in pi over 2 into sine, I get 1. So this becomes 1 squared, and cosine of pi over 2 is 0. So that's the upper limit. And then on the lower limit, sine of 0 is 0, cosine of 0 is just 1. So I'm using brackets here carefully to try not to make a mistake with the minus signs in the algebra here. But I believe that just comes out to 5. Can anybody confirm that? Okay. Okay. So we got 5 for that numerator of my cosine of theta formula. For the denominator, you have to do the norm of f and the norm of g. Maybe I'll do the norm of f, and then I'm going to leave you guys to try the other one. Blake?
Is 2 sine x cosine x, the trig identity that you're using is sine x squared?
No, there is a trig identity. I'm actually not using a trig identity for it. I'm just using a u substitution where I just let u equal sine of x and du is cosine of x. There is a trig identity for it, and if you used it to solve that integral, that's also fine. I just am trying to avoid trig identities too much that are not really at the forefront of our thinking here. Okay, so for the norm of f, I have to take the square root of the inner product of f with itself. So that would be the square root of the integral from 0 to pi over 2 of sine squared of x dx. So sine of x times itself. That'd be sine squared of x. If you're not sure how to do that, again, this is just a trig thing. What you can do to do this integral, I'm sure you learned it back in calculus, but it maybe has been a while. This is best done using a trig identity, which is 1 minus the cosine of 2x all over 2. So you could use that identity to help you simplify this one. And I need a little bit more room, I think. Let's just go back over here. Yeah, so we have the square root of the integral from 0 to pi over 2 of, and then I'm going to make a 1/2. I guess I could just pull the 1/2 out, right? Just pull the 1/2 outside, and then I'm sorry, let's erase this. I'm so sorry. I'm actually just going to do the integral. Okay, so the 1/2 can just be written down, and then all I'm left with is integrating 1 minus the cosine of 2x. So that's just going to be x minus 1/2 of the sine of 2x, I think. And that'll be evaluated from 0 to pi over 2. So you have to work this out. When you plug in the lower limit, nothing happens. You just get 0. Sine of 0 is 0. For the upper limit, let's see, square root of 1/2, and then we have a pi over 2 minus, sine of pi. Sine of pi is also 0. So there's nothing else to write down. And so this is the answer. It would be the square root of pi divided by 2. That's the norm of f. And then you've got to do the norm of g. I'll start it for you. Maybe I'll let you I don't want to steal all of the fun. But basically, this one is going to be, again, the square root of the integral from 0 to pi over 2 of 2 cosine x plus 4 quantity squared. Right. And I would recommend for this integral, you could just multiply it out. Just expand this quadratic out into 3 terms. And there will be a cosine squared term. So just to remind you, when you get to the cosine squared, the trig identity for that one that you're going to want to use is 1 plus cosine of 2x all over 2. So just a little bit of trig in the middle of our semester here to do this one problem. So I'll let you finish that one. If anybody works it out and wants to check their answer with me, I'll be around later. You can just stop by. I've got the solutions to this, but we've done most of it, right? We've got the 5 on top here. We've got a radical of pi over 2 for the norm of f, and now we just need to figure out this other number to put right there, and that's not anything too interesting. Okay. Great. That's number 4. Yeah, so the other one, Audrey, you had mentioned that you just forgot to put down 32. There's 3 parts to 32.
I found
Oh, you're actually good. Okay. Oh, no problem. Thank you for clarifying. Does anybody have any other questions on the homework for tonight that they'd like to ask me for now? Not so much. Okay, well, we don't have enough time to do group work today. We only have about 8 minutes. Let me just briefly tell you where we're going to go next, which is we're going to start chapter 6. The first section of which is will be on your exam. But I think I'll just do 5 minutes of notes here just to start this topic. This will not be anything you have to worry about until next week, but let's just start the topic of chapter 6. It is called linear transformations. So this is called linear transformations. And I know some of us are growing a little weary of the linear algebra. We're ready for differential equations again. We only have a couple more chapters of linear algebra to go, and then in November, we're gonna be getting back to the differential equation. What this is about is up until now, we have been studying properties of one vector space at a time. And any problem that you've been doing in chapters 4 or 5, there was only one vector space that you were looking at for one problem. It might change for the next problem, and it might change again for the next problem. But you're never looking at vector spaces kind of side by side. You're not looking for relationships between different vector spaces, right? Not in chapter 4 or chapter 5. But now what we're going to do here is we're going to do what every mathematician is always trying to do, which is to understand relationships between things. And the vehicle for doing that is, of course, a function, right? Mathematics could be thought of as the study of functions, if you wanted to really give it in a very basic language. And so linear transformations are going to be functions. They are going to be functions between different vector spaces. I'm going to write down the definition here, and then we won't have much time, and maybe I'll have time for one quick example, but we'll save most of this talk for next week. Okay, so the definition is a linear transformation Okay, so this is the word I'm defining. I always underline whatever word I'm defining, right? This is a function. First and foremost, it is a function from one vector space. I'll call it V to another vector space W. And this is written T and then colon from V to W. So whenever you have a function, right, you always try to explain what your inputs space is and what your output space is. So we might be plugging in polynomials into this function and spitting out matrices. Or we might be plugging in calculus functions and spitting out polynomials. Or we might be plugging in vectors in Rn and spitting out calculus functions, right? These are two vector spaces. It could be that they're the same vector space, actually. Nothing says that V and W have to be different from each other, but these are two different universes where we have inputs and outputs that go between the two universes. But it's not just any old function. I'm not done with the definition yet. It's not just any old function. There are a couple of rules about this function that I need to add to our list here. The first one is that T of V1 plus V2. So if I plug in a couple of vectors from the input vector space and I add them together, so if I do T of V1 plus V2, that should be T of V1 plus T of V2. And similarly, if I do scale, the other operation that we do in a vector space is scalar multiplication. So if I had, let's just say K scalar multiplying V1, then the transformation of that, T of that, should be K times T of V1. And these two statements should be for all scalars K and for all vectors V1 and V2 from the input vector space capital V. So the V1 and the V2 belong to V. They are elements of V. So these are the two conditions, A and B. And the way I like to refer to them casually, I will refer to these casually in the following way. The first property is basically telling us that T respects addition. The T should respect addition. You should be able to split it apart, as I just described. And the second property is basically telling me that T respects scalar multiplication. This is going to remind you of back in chapter 4 when you were being asked to show if something was a subspace or not. There were two parts to that as well. Closure under addition and closure under scalar multiplication. Now in this linear transformation world, what we're going to be doing quite often is checking whether T respects addition or whether it respects scalar multiplication. Let me just finish by writing down one example of this, and then we'll do many more examples next Tuesday. But a quick example of this might look something like this. I could define T from M2 of R to R. So I'm just making one example of a linear transformation. Now that's telling me what my input vector space is, which is the 2 by 2 matrices. My output vector space is just the vector space of real numbers. And now I have to actually give you the formula. So now I have to tell you, well, what is the formula here? T of, what do I do? If I take a 2 by 2 matrix and plug it into T, right, I'm going to give you a formula. And the formula I'm going to give you here is A plus D. Actually, let's make that A plus 5D. A plus 5D. Right? And so what I could ask you here is I could ask you to show that T is linear. We could try to show that. When I say linear, that just means linear transformation. So if I say show that T is linear, I just mean show that it is a linear transformation. You'll see me abbreviate it like that quite often. And so there's two things we have to do here, right? We have to show, first of all, that T respects addition. And then secondly, we have to show that T respects, actually, we would need a little more room than that. Then we would have to show that T respects scalar multiplication. So that is what we would need to do. But I am going to leave this. Can you guys keep your notes just like this for 5 days? 5 days from now, what I'm gonna do next Tuesday, I'm gonna come back in and I'll probably write this up and we'll actually do the verification. We have to show these two properties. Don't worry about this so much over the weekend. Your big plans for the weekend, guys, are going to be, make sure you understand the Graham-Schmidt process. You're good with chapter 5. I would love everybody to come in here on Tuesday feeling really good about chapter 5. And if you have a little time, take some of those midterm resources. Get a little head start on studying for the exam. Okay, that's it for today. Thank you so much. Look forward to the next time.